Now, let's say, so we saw how we can read the entire file, how we can write the entire file. But let's say we don't want to read the entire file. We just want to read entire file sequentially from all the way from beginning until the end, which could be done by this set of system calls. But we don't want to do that, but rather we just want to read randomly at a particular offset inside the file. Then what do we do? So how does these random reads work? So this, you can visualize it as, for example, when you have index in your textbooks, it helps you to go to exactly the topic that you want to read about, right? So in the same way, if the files have a notion of offset, that offset will help us to go to exactly the content that we want to read or write or access. Now, let's take an example of command offset lseek. This is the command on Unix system that allows us to access any random offset inside the file. So what does this command takes? First, it takes file description. So file descriptor. Now, as you already know, all the open files has a unique file descriptor inside the process. Second, it takes offset. So this is offset to particular location within file. Third, it takes this command called int vents. Now, what is this int vents? Well, that determines how seek should perform. How does it determine how seek should perform? This command vent has different options, such as if vent is seek set, then the offset is set to offset bytes. So whatever we give here in this offset will be set exactly to that amount of bytes. And we would start from the head of the storage device. If this vent is another option called seek cur. Now in this case, the offset, this one, is set to its current location plus the offset bytes. This is useful while doing an implicit access to the file, right? So if you want to do an access iteratively, then we would have this notion of current pointer. You read a particular portion, so then your offset is incremented from the current pointer with that particular portion. So seeker is a pattern that's used for such implicit access. And another option that it provides is seek end. What seek end does is it sets the offset to the size of the file plus the offset bytes. So it goes to the size of the file. That means the end of file plus the offset bytes. That's what seek end does. So depending upon what we set this third argument to, this offset is determined based on that. As I already mentioned, that in some of these options could be useful for an implicit access. Definitely, you might be already thinking that if there is an implicit access, there is an explicit access as well. What is explicit access? Pretty much any access given by the user to access a particular offset is an explicit access, right? So if I know that I want to access the 5th byte stored in the file, then that's an explicit access. So it just returns that. And maybe for such an explicit access, I want to, if my current is pointing to the head of the file, then I can use seek current with that offset of 5 bytes. If I know that this file is the first file, then I can directly use seek set with that 5 bytes as an offset. So offset is maintained in the struct file that we saw earlier, where we saw a process that has a struct for each file inside that process, inside struct for each open file inside the process. Now, what does the struct file consist of? So as a simplistic example, again, it depends on different operating system. If you are designing an operating system of yourself, you can definitely change the content within the struct file. Or even if you're designing a file system of your own, then you can definitely still change the content inside the struct file, right? So this is just an example of a Unix file system and a very basic one. So at the minimum, it should contain things like struct file, should have int reference. We will soon see a usefulness to this variable reference. Char readable. If it's readable, pretty self-explanatory. Char writable. If the file is writable. It contains the struct inside it, struct of inode, pointer to that struct, and it contains unsigned int of offset. So at the minimum, the struct file consists all this information about the reference, the type of it, readable or writable. It contains the struct inode and the pointer to that struct. And it finally contains the offset for that file. So a very important thing to remember is the command lseek that we just saw over here. This lseek does not perform disk seek, but rather it just determines next position to read or write from file in memory. And one more thing, we maintain a structure of open file table. This open file table is used to maintain offsets individually, offset buffers individually for each file with different entries. So two different applications can open the same file with read-only permissions, and they could read the same file in parallel, right? So in that case, this open file table will have entries for both these files with where each of these applications are. So an application 1 could be reading the first line in this file, while application 2 could be already reading the 10th line in this file. So this open file table helps us to maintain such offsets for each open file. Now, sometimes in corner cases, it happens. So mostly all the applications, it opens the file first, then it either accesses, so either reads or writes to that file, and then closes the file, as we saw in earlier examples. But sometimes it could happen that this open file table has two different files referred by the same entry. And it is very rare. It could happen in the scenario such as if we are using functions such as fork and dup, and its subsidiary versions such as dup1, dup2, etc. So what happens in this case is we could have shared file table entries inside the open file table. Can you think of why? Let's say that this is our open file table. It has multiple entries. One of the entry is, so each entry stores the reference count, offset, and the pointer to inode. Now, this is exactly what the file struct stores, right? The information that it stores, such as this. This pointer could refer to some inode, let's say inode number 1000. And it's storing file.txt. It could happen that we have a pointer to this particular entry in open access table from a file, again opened with a file descriptor number 3. And file descriptor is unique, right? Now, when we fork this file, then what happens is we would increase our reference count. So initially, if the reference count is 1, now when we fork it, it's increased to 2. here is where the reference variable is used. We would have the same offset shared by even the forked file, and they share the same inode. The forked file, which is, so this is the parent process, and after the fork, this is the child process. It also has the same, exactly same file descriptor. So both this parent process and the child process are pointing to the common or the shared entry inside the open file table, which shares the same inode. These are the rare cases where we could have multiple files sharing the entry inside the open file table. In the same way, for the dupe operation as well, the same scenario could happen. So for example, now, let's say when we delete the parent process or delete the child process, one of that, then this reference count will be decremented by 1. And finally, only when the reference count is 1 and exactly 1, and that file is then deleted, that means that now these entries are free to be removed or deleted. Until then, until a reference count is anything greater than 1, until then, although just the file is deleted, but the content referring to the structure of that file, the inode of that file, this helps us to keep a track that, hey, this entry was also used by another file. So this entry is not yet ready to be deleted, although this file, one of the file that was using this entry is deleted. Now, this kind of structure or this fork process is mainly used in shared system programming languages, such as like shared memory programming, such as OpenMP. If some of you are already familiar with using OpenMP language, then you know that in OpenMP, you can have a parent process and then you can fork child process from the parent process. So exactly when you do that, this is what is happening underneath the hood inside the system. Now, coming back to now, we saw the different operations of reading, writing in a sequential fashion, in a random fashion for files. What happens about directory? So reading directories. It is simple enough, just a very simplistic command on a Unix system. So in your terminal, when you issue commands such as lsdir or a command such as ls-l file details are revealed on the console. So you can try something right now, such as strace. Try strace on ls as well as on ls-l. What happens? What are the output that you get on your console? That gives you, there is an A right there. So it would give you exactly how directories are read in the system, the underlying steps for that. Handling directories are way simpler than handling files, right? Because one major difference between files and directories are that we do many more operations on files and much lesser on directories. So here comes your first question for the discussion post that you're supposed to write for this lecture is mention or identify difference between file descriptor and inode number. So we learned that every open file has a unique file descriptor inside the process. So that mentioned the difference between that file descriptor. And we learned that every file has a unique inode number right at the beginning of this lecture. How are these both different? Elaborate on your understanding about that. That's your first question. The second question I have for you is about what is it or what basic operation that we can do on files, but not on directories. So we talked about different basic operations about creating and accessing files, creating and accessing directories. Now think logically, what is an operation that we can logically do on files, but doesn't make sense to do on directory? Write your description, elaborate your reason why you think that in the post.